afternoon, everyone. So today I'm going to talk about experimental commitment of distribution grid with high penetration of photovoltaics using high resolution prediction algorithm and storage. We start with the motivation. For motivation, we have mainly 4 topics. We start with renewable resource, always change often, so it's uncontinuous to supply the load. As you can see, it's swing all the time. The next one is about the how swing of rooftop PV always affect the transmission system, because it's always sometimes like have a high spike that create overvoltage to the transmission system. Next, motivation is about we want to improve cost effectiveness of BSS, and we want to avoid use of expensive generators because BSS is lower cost than generators. And the last one is about we want to use a better forecasting method to reduce unnecessary costs, because if we have a clever or a useful forecasting system, we can optimize operation more accurately and can reduce any cost that is going to happen in the system. Next is our problem statement. I'm going to mention first what is a BSS and what's a SOC, because it's going to appear all in my slide. First, about the BSS is a battery energy storage system. It's a system that's used a pack of the battery store the energy from the renewable resource and the state of charge. The state of charge is about you show the total capacity that is contained in one single battery. Next, we're going to talk about many topics. We want to optimize BSS to control the unpredictable fluctuations. And we use 2 methods to control this. First is a peak shaving. Why we use this method? Because in the actual load, the spike is really high during the day because the peak demand is so high. So we want to cut the peak off because the higher the peak, the more power we have to produce. So if we cut the peak off, we can reduce the cost and the power that we have to produce. And why we study the peak shaving? Because we want to study the charging characteristic of the battery. Because sometimes renewable resource always produce exceed power. So we need to store it for later. And we want to study the discharging characteristic. Because sometimes we want to use store energy from the battery. So we need to discharge it to help supply the load during peak demand. And we want to reducing the high cost generator because we want to focus mainly to use BSS instead of the expensive generators. Next is smoothing. Why we want to smoothing the load? This is the example of the smoothing. The blue one is an actual load graph, and the yellow one is a smoothing one. Why we want to smoothing? Because all days we have a fluctuation. The fluctuation is like an oscillation of the graph that's happened all the time. And it's make the load that's slightly different to supply. The reason why we want to smooth because we want to we want to smooth the graph of the actual load to produce the same amount of the power all days. And why we want to use this method? For smoothing, we want to reduce power inconsistency, and we want to stabilizing midday fluctuation. Next is a proposed solution. This is our system. We have a rooftop PV, transformer, BSS, and hybrid forecast and load commitment program, or HFALC. This is the main central hub that used to control the forecasting method. And the energy management system, EMS, is used to control the BSS or office island grid. And this is our power system model. Next one, we talk about forecasting framework. We simulate this experiment for 108 days for 24 hours. We have 2 methods. First one is a parallel. Next one is series parallel. For the parallels, we create linear regression models. This is the example of linear regression models. We have a sample data and the line. It's a regression line. And use 100-day historical data. The next one is a series parallel forecasting. It's more efficiently because we use a small interpolation and pass 20 minutes of historical data to reduce prediction errors. This is a framework of this model. It's a forecasting method it's installed in HFALC. Send the data to the EMS, and when EMS just calculate the data and we send it to the optimization, the batteries. Next, we have two methods, approach 1 and approach 2. For approach 1, we use a nonlinear programming plus parallel forecasting to plan an SOC schedule for peak shaving. And when we got SOC schedule, we use for control the short-term fluctuation for smoothing. In the other one, we use a real-time integrated controls. For the real-time integrated controls, we use simple algorithm. This is the example of simple algorithm. It's like you just create a flow chart for the algorithm and let it calculate for a loop until it get a good result. And use a series parallel method to control peak shaving and smoothing together. And also we track the adaptive slope reference line, or it's a spiraling interpolation on this slide to keep the BSS chart fully all the time. Next one, we move to the result. From the result, we can see that BSS is effectively control the grid demand, but I will show you later from this slide. We will focus on the forecasting accuracy first. On the forecasting accuracy, the series parallel method is better than the parallel forecasting method. As you can see, the red line is an actual load that's happened in 108 days, and the blue one is a load that is forecast by two different methods. And you can see that in a parallel forecasting, load is not exactly the same like the series parallel forecasting method. That we can clearly see that series parallel forecasting method can forecast more precisely than the other one. Next, we talk about the method comparison. When we compare the both of approach, we can see that approach 1 can reduce peak demand is smooth, but it's not in accuracy. And the second one is more effectively in peak shaving smooth. Why is that? Why its approach 1 is more bad, more worse than the other one? As you can see, they have some spike that come from nowhere, but in the approach 2 have a less spike than the approach 1. And for the fluctuation, for approach 1 cannot control better than the approach 2. The approach 2 have a better result of a peak shaving and smoothing. Next is a system reliability. It's when we use a real-time control with accurate short-term forecasting can help manage fluctuating. We can see that in approach 2, we can control the chart, the SOC leverage better than the approach 1. And for the result, series parallel is better than parallel because it's more precise prediction. For the experimental method, approach 1 is better than approach 2 because it's more accurate, give a better result, and perfectly handle fluctuation. Thank you.